So now we continue with the last part of this particular chapter, refraction through lenses. This is about magnifying glass and the application of the lenses. So first of all, we will understand how is the magnifying glass being used, and you will see a small ray diagram of the same. So we know that magnifying glass is basically a convex kind of a lens, and here magnifying glass will be the one in which the case of the ray diagram will be the one in which the object is placed between F and O. So that is exactly what will be the ray diagram what we are going to be drawing for this particular application. So magnifying glass or simple microscope's principle to observe a tiny object distinctly. We prefer to place it as near to our eye as possible. But to see an object by the naked eye, it is necessary to place it at a distance of 25 centimeters from the eye, which is the least distance of distinct vision for a normal eye. Thus, an object is seen distinctly and of a maximum size when it's placed at a distance d from the eye. So, see, in our eye, if I keep anything so close, I will not be able to see it clearly. For seeing anything clearly, I need a minimum distance of 25 centimeters between the object and my eye. If I place anything at a distance of 25 centimeters over there, then I can see something most clearly. So that is why it is called as the distance of distinct vision. The distance of distinct vision is 25 centimeters from eye. Okay, that is the distance of distinct vision for a normal eye. Thus, an object is placed at a maximum size or for a maximum size. If I want to see something at a maximum size, I will place it at 25 centimeters, provided I am having normal eye and I am not having any. Like suppose I have spectacles but I am not using it and I keep it at 25, I may not be able to see something properly if I have got long-sightedness. Okay. The size of the image of retina is actually determined by the angle subtended by the object at the eye. Smaller the angle subtended by the object at the eye, smaller is the size of the image on the retina. The eye is not able to see an object distinctly if it is subtending an angle of less than 1 degree at it. To observe a small object with subtended angle smaller than 1 minute at the eye, when we place at a least distant receiving vision from the eye, we take the help of a convex lens of short focal length. So what we are going to do is, if we want to view something slightly magnified in a proper manner, we normally use a convex lens and of a shorter focal length. So a shorter focal length will magnify it much more. So that's why we are going to use a thicker lens, that is shorter wavelength. Focal length का ये. We hold the convex lens in front of the eye at such a distance that the object lies within its focal length. So the lens forms an erect, virtual and magnified image on the same side behind the object. So we are going to place suppose I want to read. Okay, I will take this example. I want to read this. So what I'll do, I'll take a magnifying glass and place it over here, close to this thing, so that I can get the image of this thing on the same side of the object, a bigger one on the other side of the lens, which I can read it much bigger. Okay, so we hold the lens in front of our eye at such a distance that the object lies within its focal length. So the object will be within the focal length of the lens, so that the lens forms an erect, virtual and magnified image on the same side and behind the object at a distance d from the lens. This magnified image now subtends on the eye an angle greater than 1 minute, so it distinctly seen by the eye. This is the principle of simple microscope or magnifying glass or reading glass. Construction: a simple microscope is convex lens of short focal length mounted in a lens holder as shown. Way of using microscope: the lens is placed near the eye and its distance from the object is adjusted such that the image is formed behind the object at a distance d from the lens. where D is the least distance of distinct vision, is 25 centimeters for the normal eye. So I am going to place it in such a way that the image which is going to be formed will be 25 centimeters from my eye, okay, so that I can see the image most clearly. So for the ray diagram, so it's a simple ray diagram. What we can draw is this way. We have got the same thing what we had drawn yesterday. This is last time. This is your 2f1, f1, okay, and that will be the lens. We will place it over here. Okay, I'll place it in such, yeah, I'll place it here. This is the lens, so this is O, and this is f2. The object will be placed somewhere here. This is where the object is going to be placed. The lens will be of this kind. This is the object A, B. So as usual, we are going to take two rays. One ray which is going to be passing through O. So a ray passing through O like this, undeviated, and another ray which will be parallel to principal axis, which on passing the lens, it will pass through f2 in this manner. So accordingly, this, when you are taking it backwards, will intersect at a point here. So the image will be a virtual image but magnified image over here, A dash, B dash, which is virtual, erect, magnified. Okay, this is the kind of image which will be given on the same side of the object, behind the object, which will be virtual, erect and magnified. So this is what the figure will be like for magnifying glass. What is the magnifying power? The magnifying power of a microscope is given as m is equal to 1 plus f d upon f. So it is given as magnifying power is m is equal to 1 plus d upon f. This is the magnifying power, where f is the focal length of the lens and d is the least distance of distinct vision, 25 centimeters for normal eye. The magnifying power of a microscope can be increased by using the lens of shorter focal length. Shorter the focal length, more magnifying the power, but it cannot be increased indefinitely. So of course you need to, you can increase it to a certain extent, but you cannot take it indefinitely. Example, the magnifying power of a convex lens of focal length 100 cm is 1.25, while the convex lens of focal length 5 cm is 6. So yeah, you can see that focal length is more, then the magnification is less. Focal length is less, the magnification is more. That means thicker the lens, more the magnification. Uses a simple microscope or magnifying glass is used to see and read the small letters and figures. It is used by watchmakers to see the small parts of the screws of the watch. In optical instruments such as a traveling microscope, spectrometer, etc., a magnifying glass is provided above the vernier scale so as to read the scale accurately. Hence, it is also called as reading lenses. So you can see that magnifying glass is used in many places. In fact, you would be many of the watches, if you see the watches, of course not, I'm not wearing it, but the watch का जो ऊपर का जो glass है, sometimes it is made up of a magnifying glass. It is thicker so that अंदर का जो dial का जो part है, it is more magnified. So that is why the glass on the top is made thicker so that it acts as a lens. Okay, and apart from that, you must have seen the watchmaker wearing that cup like this over here, which has got a magnifying glass. So when he puts a cup over here and then sees your watch and repairs it, so that is nothing but the magnifying glass. So the application of the lenses are used in large number of optical instruments. Some common applications are given below. The objective lens of a telescope, camera, slide projector, etc. is a convex lens which forms the real inverted image of the object. In fact, last time when we are doing the ray diagrams of the lenses, at that time I told you to write the uses also at the same time. So you can see that all these uses were already mentioned over there in that particular ray diagram. Our eye lens is also a convex lens. The eye lens forms the inverted image of the object on the retina. Okay, so whatever we are seeing, actually our object, that object is being given an image where this, what we are going to get on the retina will be ulta, but the brain then interprets and makes it sida. When our eyesight's weaken, we use spectacles having either the convex or concave lens. A person suffering from long-sightedness or hypermetropia, that means he is unable to see near objects distinctly, wears spectacles having the convex lens, while a person suffering from short-sightedness or myopia, unable to see far off things distinctly, wears spectacles having concave lens. So if somebody cannot see something near, he will use a convex lens. But if he is not able to, he's able to not able to see. So long-sightedness means he can see the long things but cannot see the shorter things. So when he's not able to see the shorter things, he will use a convex lens, converging kind. And if he's not able to see the near far off things but can see the near things, okay, he will be using a concave lens. Some people are both short and long-sighted. They use either the separate spectacle for seeing the near and the far, or use a spectacle with a bifocal lens. In the spectacle using bifocal lens, the lower part is convex, which is used to see the near parts, while the upper part is concave, which is used to see the distinct objects. So you must have seen many of the people in the age group of your grandmother and all, or not only grandmother, even your father may be wearing it. He will be using a spectacles which has got the lower part being thicker and the upper part being the one which is rough. So he has got both the problem with the vision. So if you can see that for reading, he will be using the eye downwards and reading it. So because the glass over there, so if this is the spectacle, so if this is the spectacle, then this much part over here, that will be thicker for reading. So this is for reading, and the upper part is for viewing distance object. Okay, so that's called as a bifocal. So bifocal means lower part for reading, and for far off things the upper part, because normally when you're going to see something far off, you're not going to look like this, okay? You're going to look straight. But when you're going to read, you're not going to, well, you are going to read like this. So you're going to do it like this, so the specs will help you to do this way. Right, so a magnifying glass is a convex lens of short focal length fitted to a steel frame or plastic frame provided with a handle. In a colorimeter of spectrometer, convex lens is used to obtain a parallel beam of light. A concave lens is used as an eye lens in a Galilean telescope to obtain the final erect image of the object. And finally, a single convex lens usually forms a colored or blurred image due to chromatic aberrations. Therefore, a combination of concave lenses with a convex lens is used to overcome such defects. So many times, because there is a kind of a prism formed over there, there will be a form of a colored or blurred image formed by the single convex lens. That's why there will be always a combination of convex and concave at those areas, so as to overcome the defect of coloration. Now we see some experimental determination of the focal length of a lens. So we are going to see that how we are going to measure the focal length of a particular lens. So it's a very simple thing as such, because here let me see if I am able to get this thing over here. Now I got this here, this is the magnifying glass. This is the magnifying glass we are talking about. So this magnifying glass, when I place it over here, it will be seen that there will be an image which is formed over here. Now, the moment I get a very clear image over here, see whatever is on this side, I'm going to get an inverted image. You can see over here there is a tube light over here. So this is, you can see inverted image of The tube light is above there, but I can see it over here. So this is the inverted image of the tube light. So when I can see the image very clear, at that point, if I measure the distance between the lens and the screen, then I can say that distance over here is nothing but the focal length. So that's what they are given over here, that they are taken a scale. They are taken a scale, so I can also take a scale like this. So I too can take a scale like this, and then I can place this thing over here, and at a point where I can get the right image of the this tube light properly, then I can take that particular point as the focal length of this particular thing. Now normally it will be better if I take a place where the sunlight is coming up. So when sunlight comes up, then I can get the image more clearly and I can identify the things. In fact, if you see in front of a window, you will come to know that window के बाहर में अगर tree वगैरह रहेगा तो it will be upside down. So you can try the thing at home, because I cannot show it over here because even the video will not be proper to show you that thing. So, or you can remind me when you come to the class next time. At that time in the class, I can show you that exact image which is formed by the lens, right? So you can see that the method is very simple. Principle is that the beam of parallel rays from the distant object incident on a convex lens gets converged at the focal plane of the lens. So we had seen that when you had got the object placed at infinity, so because the object was placed at infinity, the image which was formed was at f2, or the focal point, or the focal plane. So if it is at far off object, or if it is say at infinity, you are going to get the image at the focus. So when you get a clear image, that means your lens is at a distance such that the lens and the screen is at the focus. So accordingly, the distance between the lens and the screen will be the focal length of that particular lens. So accordingly, we have this particular figure. So they have given you this particular figure. That image of the tree is inverted over here and the lens is placed on a scale. So as you move the thing, if you get a clear image here, that means at that particular point, that distance over here, for example, in this case, the distance is 48. So 48 is the 48 centimeters, the focal length of this particular thing. So in an open space against a white wall, place a meter rule horizontal orbit at 0 centimeter touching the wall, and its other end towards the illuminated object, which is at a very large distance, such as a tree or electric pole. Holding the given lens vertically on the meter rule, focus the object on the wall by moving the lens on to and fro from the length of the meter rule. Since the light rays incident from the object, distant object, are nearly parallel, the image of it formed on the wall is almost at the focus of the lens. So read the distance of the lens from the wall directly from the meter rule. This gives the approximate focal length of the lens. Figure shows the formation of the image of the wall of the image of the wall on a distant tree situated on the left of the lens, which is not shown in the figure. The approximate focal length of the lens is 48 centimeters. The ray diagram is shown in figure 5. So we can see the ray diagram. So it's a simple ray diagram. This is the lens over here, and these are the rays of light coming from infinity. They are going to converge at a point over here, this particular point. So this distance from this point to this point is nothing but the focal length f. So that is what is given over here as the formation of the lens, or the calculation of the focal length. You can also have another method also, determination of exact focal length at an auxiliary plane behind a mirror. So what you can do is, you are going to place a mirror, and to the mirror you are going to place the lens, and then on one side you are going to place, so it is going to be this way. I'll show you a figure. So we are going to keep a stand, and to the base of the stand we are going to place a mirror. So this is the mirror over here, and to this mirror you are going to place a lens. Okay, this is the lens. Over here you are going to take a pin. Okay, this is a pin what you are taking, which can be adjusted. The location of this can be adjusted. You will find that at a particular point, you will find an image of this pin over here when viewed from the top. This is the eye. This is the position of the eye. You will be seeing an image of this thing over here, like this. At this point, this distance over here is the focal length. And why would this happen? Because of the ray diagram. यहाँ से ray इधर गया. Okay. And from here also the ray went here like this. They went here. They went straight because it is a focus. At focus, it becomes parallel to principal axis. Once they become parallel to principal axis, it is returning the same path. It returns back into the same path. So this goes like this and goes here, reflects back and returns in the same path. So that's why you get all the object over here. Uska image मुझे यहाँ पे मिलेगा. So that is how this is the pin and this is the image. Okay. So this is how you find out the thing. So place the lens L on a plane mirror, mm dash kept on the horizontal surface of vertical stand, and arrange the pin P horizontally in the clamp so that its tip is vertically above the center O of the lens. Adjust the height of the pin till it has no parallax with its inverted image of it as seen on the vertical above the pin. To check the parallax, keep the eye vertically above the tip of the pin P at a distance 25 centimeters from it and move it sideways. If the pin and its image shift together, there is no parallax. Measure the distance x of the point P pin from the lens and the distance y of the pin from the mirror using the meter rule and with a plumb line. Calculate the average of the two distances. This gives you the focal length of the lens. So yeah, this is, what you are going to do is this distance. Now this distance over here will be taken as x, and this distance will be x, and this distance from here to here will be y, and focal length will be x plus y upon 2. Okay, that will be the x plus y upon 2. Take 3 different observations after removing the parallax each time and find the mean focal length. The alternative method could be the same thing can be made. This is like sleeping, you can make it standing also. So you have got a table here, and to this table you are going to have the stands. So in one stand there will be this pin. So this is one pin which is going to be there in one stand. To another stand over here there will be a convex lens, and then on another stand will be a mirror. So according to the same thing happens. So this is going to be, the pin will be up here. So this pin will be like this, going like this, इधर जाएगा, फिर straight हो जाएगा, because parallel to principal axis. It will return back in the same path. Accordingly, you will get the image of this pin over here. Okay, so then this becomes the focal length. Right, so that is what you are given over here. The above experiment can also be performed by using pin and convex lens and the plane mirror fixed on the separate vertical stand of an optical bench. We proceed as keep the lens L close to the plane mirror M, adjusting the height of the object P such that its tip lies at the center of the convex lens. So you adjust it that this lies at the center over here. So that is what you are adjusting it as. Move the object O away from the lens on the optical bench till its inverted image is viewed by keeping the eye behind the object P at a distance of 25 centimeters from it. So you're going to keep the eye at 25 centimeters from here and then check it. Now adjust the position of the object P O by gradually to and fro movement of it so that the tip of the inverted image I coincides with the tip of the object P O. So you are going to see to it that when you move it, we are going to make arrangement in such a way that this image and this pin are exactly one above each other. Now adjust the image, so that the tip of the inverted image I coincides with the tip of the object O. In this situation, moving the eye sideways, both the tips of the object and the pin will appear to move together. So note the position of the object P the say x1 and position of lens x2 from the optical bench. The distance x2 minus x1 gives the focal length of the convex lens. So here it is, x1 is 30 and the x2 is 60. So accordingly f is 30. So explanation towards this thing is, when the object pin lies in the focal length of the lens L, the rays of light starting O after refraction from the lens become parallel to the principal axis. So whatever is starting from here, it is going to go here, and because it is at F, so any ray of light passing through F becomes parallel to principal axis after refraction. So that is what is happening. Therefore, they strike normally on the plane surface behind the mirror due to the normal incidence. Because it is normal to the mirror, it is going to reflect back in the same line. So the rays of light reflected back on the plane mirror on the same path, and then they re-enter the lens as a parallel beam. The lens converges this rays in the focal on its focal plane, thus forming the image I just above the object P pin O. The image I is inverted, real, and same size as that of the object O. So figure shows the ray diagram. So that's why we can see a simple ray diagram over here of this particular thing, that you have got this lens, you have got this mirror, you have this point O, this is the rays which are passing from F over here. So this becomes parallel to principal axis, and then it is going to come back, then it passes through focus. That's why it is landing up over here like this. So that's why this is the image and this is the object. Note the position of the plane mirror relative to the lens. So the length Lm does not affect the position of the image as long as the rays of the lens fall normally on the plane mirror. However, the plane mirror M is kept close to the convex lens so that the image I can be distinctly seen. So here, even if I move this mirror far apart or I bring it very close, there would not be any effect over here, because here it is just a parallel line. So that's why this distance is not going to make it. We are going to keep it close so that it can be easily seen. There is no loss of the energy which is going to be there from the reflection. So to avoid that loss, we are going to place the lens and the mirror quite close to each other. Now we see to differentiate between the convex and concave lenses. So first is by touching method. If the lens is thick in the middle and thin at the edges, the lens is convex. And if the lens is thin in the middle and thick at the edges, the lens is concave. Okay, so if you touch it and you feel that, जैसे मैंने ये पढ़ा, यहाँ पे I can feel this is thinner and this is thicker, so this is convex. Okay, so by touching you can make it out whether it's a convex lens or a concave lens. If the thicker part is in the center, it's convex. Thicker part is at the edges, it is concave. Or seeing the image on keeping the lens near a printed area, if the letter appears magnified, the lens is convex, and they appear diminished, then it is concave. So if I place it over here, you can see that you are able to see a magnified image of this thing. So you can see a magnified image. So that's why it's a convex one. But if it would have been a concave, then it would have a diminished image, what will be seen over here. So if the letter is diminished, then it is concave. If it is magnified, it is convex. On seeing a distant object through the lens, if it is inverted image is seen, the lens is convex. And if it is upright image is seen, it is concave. So again, one more thing, if something is at a distant object and you are trying to see and the image which is formed is inverted, then that particular thing is a convex lens, and if the image form is erect, then it is a concave type of lens. So this was the end of the chapter refraction through lenses. So this was including the numericals, everything is over. So that was the end of the chapter refraction through lenses.